Welcome back to ECE 541A, 441A. What we want to do, I really don't have too many announcements today other than there are a few delinquent passports, and you can check D2L to get those created. I haven't closed the Dropbox, hopefully, if you're still not yet on board with your passport. What I want to do today is, as promised, talk about 3 different ways of creating a transfer function. One from differential equations, which we've actually already done, a block diagram procedure for finding the transfer function, and then we'll spend a little bit more time, or it will take a little bit more time to develop the connection between the state space representation and the transfer function, and we'll do that in general. Then we'll start setting some things to 0 that we are not needing at the present time. And then we'll look at a Bode plot, or maybe several Bode plots, depending on what values of M, B, and K, and I guess gamma, if we introduce a gamma term. And then we'll move on to another set of equations, and those will be arising from a 3-mass system that's connected differently than what we might be thinking from just this basic mass spring damper system that we've been playing with up until this particular point in time. Let's then get started with deriving this transfer function relationship for the different systems, or actually this one system. With this mass spring damper system that we have the differential equation, which was m times the acceleration plus the dash pot coefficient b times the velocity plus kx, which is the spring force, and then that's times gamma u. And this is then the time domain expression that governs the dynamic behavior of that mass spring damper system. What we want to do first is find the transfer function of this based on this differential equation, and the way to do that is to take it immediately into the frequency domain from the time domain. And since we are interested in input-output behavior, we're not going to worry about the initial conditions when we do this Laplace transform. If we now Laplace transform this, we end up with m s squared x of s plus b s x of s plus k x of s equaling gamma u of s. We can now factor out the common transformed quantity, capital X of s, and we have m s squared plus bs plus k all times x of s equaling gamma u of s. And if we solve that for the ratio x of s over u of s, that will give us our transfer function g of s, which is now this gamma over ms squared plus bs plus k. And we've maybe written that differently. We could have said, well, let's normalize the denominator polynomial. Let's make it monic, which means let's make the leading coefficient of the highest power of the denominator equal to 1 by factoring out the m from all the terms and pulling that m upstairs. And you maybe remember that we wrote that transfer function in that particular manner. That's the first way of obtaining that transfer function, and that's from the differential equation, just Laplace transforming and solving for the ratio. Let's now look at the second approach, which is by examining the block diagram, and I'm going to just recall what that was from last time in the frequency domain. We had two integrators, which in the frequency domain are these 1 over s blocks. Then we had this feedback path from the first integrator's output in the frequency domain feeding back into this summing junction, and we had another gain feeding back the information from the output of the second integrator block. And we also had the input U of S being applied to that particular system, and this was then the transform of our position variable, capital X. What we want to do now is from this block diagram, do some block diagram algebra and define the transfer function between U of S and X of S. So I'm assuming that we had this and we could obtain this from the differential equation. That would give us the all-integrator block diagram, and then we could take that all-integrator block diagram into the frequency domain by replacing the integrator blocks with these 1 over s blocks, which are what they represent in the frequency domain. Now, in finding or performing this block diagram algebra, a lot of times you feel like you're chasing your tail. You just keep writing equations and ending up in the same place that you started. One way to try to minimize that is to start writing equations for variables that are the outputs of summing junctions, and then trying to rewrite that expression, this W of S expression, in terms of the variables that we really want to end up with, which in this case are the output variable, which is the positions transform X, capital X of S, and the input itself, U of S. So let's now start by trying to write the equation for W of S, and if we don't have variables, let's just define some. For example, instead of circling back completely immediately, let's just go ahead and say, well, there's another signal. We'll call that X sub 2 of S. Now, let's write W of S, the output of that summing junction, in terms of the inputs to the summing junction, and we have gamma over M U of S. Then we have a minus B, well, maybe I should keep going. Let me just move in the counterclockwise direction starting at 12 o'clock. So I've now picked up the input. I can now pick up this minus K over M X of S, and then a minus B over M X sub 2 of S, and that's now a valid equation. That's the output of that summing junction expressed in terms of these different signal paths making up the inputs to that summing junction. So we have inputs equal outputs. Now what we want to do is try to rewrite some of those equations in terms of inputs and outputs, meaning U, as it already in terms of u, that's an input, but x likewise is a variable that we know. X sub 2 is one of the variables that we don't yet have expressed in terms of outputs or inputs. But if we look at this piece of the block diagram, we can find a relationship between x sub 2 and x. Meaning, using that, we can see that x sub, well, and we could also look at this particular piece. So that's what I'm going to do first. Let me now write this and say that x sub 2 of s is equal to 1 over s w of s. And we also know that x of s from the yellow highlight is 1 over s x sub 2 of s, which now says that if I just combine those, I see that x of s is related to w of s by 1 over s squared w of s. So now I've just cascaded those two relationships. Or I could say if I want w of s in terms of outputs and inputs, I now have a way of doing that. I can solve that most recent found expression for w of s, and I see that that's just s squared x of s. Just looking at this piece and solving for w. So now I have w is s squared x, and I also have from this guy right here, I have that x sub 2 is s x of s. And now I have w and x sub 2 written in terms of outputs and inputs. And since I can have that set of relationships, I'm going to use those relationships in this first equation that I wrote that was written based on that one summing junction. W of s I'm going to replace with its expression in terms of x. So I have s squared x of s, and that's equal to this gamma over m u of s. Then I have a minus k over m x of s. And finally, I have a minus b over m s x of s. I now have an equation that only contains input and output variables that are transformed. And I can collect all of those. And first, let me just clean this up by getting rid of those fractions. Let me multiply both sides by capital M, the mass. And speaking of mass, did everybody go pick up their half-gallon of milk at the grocery store this weekend to figure out? I had to buy 4 last night, so I got really good at trying to figure out what 2 kilograms is. All right, so where are we? We're trying to solve this equation. If I first multiply through by m and then pull all the x's onto the left side, I end up with m s squared plus b times s plus k all times capital X of s, and that's equal to gamma u of s. And now I have my transfer function again. I can now see that g of s, which is this x of s over u of s, is now gamma over ms squared plus bs plus k. And that's the second way of finding the transfer function. We found it from the differential equation, we found it from the block diagram, and that was just doing block diagram algebra by looking first at writing equations for the signals that come out of the summing junctions, and then try to rewrite any variables that appear in terms of outputs and inputs. Now let's look at the third approach, which is to find the transfer function from the state space representation. For the mass spring damper system, does everyone have that memorized now? As far as what we derived last time, it's second order. And these are arguments of time. Maybe I've left those out, but now this is 0, 1, this was minus k over m, this was minus b over m, and this was plus 0 gamma over m u of t. And I think we said that the position was our output variable. I'll just go ahead and throw that D matrix in there, even though it really doesn't exist in this particular example, but I'll carry it through and then set it equal to 0 at the end. There's our system matrix A. Here is our input matrix B, the output matrix C, and the direct feed-through matrix D. We now have then x prime is equal to ax plus bu, y is equal to cx plus du. And we could write that down for any linear time invariant system. It's just given the system, that will determine how big those matrices are dimensionally. If I had a fifth order system, what would the system matrix dimensions be? It would be square, and it's 5 by 5. Then I would have to tell you how many inputs I have and how many outputs I have before you could tell me what the dimensions of B, C, and D actually are. But in this case, we have a single input, single output system, and we do not have a direct feed-through element, so the D matrix is actually 0. But let's just do this in general. Let's go ahead and Laplace transform. These are now all functions of time. The Laplace transform of the output equation is trivial because they're all at the same point in time t and there's no derivative present. But let's Laplace transform the dynamic set of equations, which is the x prime equal ax plus bu, and see what we end up with. So we're going to Laplace transform the derivative, and remember x is a vector. We'll have the Laplace transform of however many components we have in that vector. If it was 10th order, then we would be taking the Laplace transform of each of those 10 components in our state vector x. Then we Laplace transform a x of t plus b u of t. And now I need that sound effect every time I want to Laplace transform. That's kind of neat. Okay, so when I say Laplace transform, you can think that sound effect, whatever that was. Maybe you're hearing, well, my hearing is going, so pretty soon I won't even hear that. Now, what happens when we Laplace transform x prime in general? In general, we have to keep track of the initial condition. So let's keep track of it just so we can follow it through and see what we end up with. If we Laplace transform the derivative, we have s times capital X of s minus x of 0 minus. And that 0 minus is time t equals 0 minus. That's not capital X at s equals 0. That's little x of t when t is equal to 0 minus. That's the initial condition of that state vector. And in this case, if it was 10th order, we would have 10 of those initial conditions. We would need to know the initial position, the initial velocity, the initial current, the initial voltage, the initial pressure, the initial temperature. If those are our state variables, we would have to keep track of those, or we would need to know those. Now, what happens if we Laplace transform the right-hand side? The A and the B are time invariant. They're constant matrices, and so the operation, the Laplace operation, slides right through those, and we now have A times the Laplace transform of x of t plus B times the Laplace transform of u of t. And that will just be then A x of s plus B u of s by definition of the Laplace transforms. If I rewrite that, then I have s x of s minus x of 0 minus equal A x of s plus B u of s. And what I want is really the input-output behavior, since I'm looking for the transfer function, and x is an internal variable. I'm really wanting to eliminate this capital X of s and just end up with u of s, capital U of s, and capital Y of s. Because I need the transfer function between u and y. And now I have this internal vector, capital X. And x in general is n by 1. But what I want to do is get rid of capital X, and now I have this s, x of s on the left, and I have a capital A, or the matrix A times capital X of s on the right. I would like to combine those, but s is a scalar. It's 1 by 1. A is a matrix. It's n by n. But I can create a way of combining those by simply introducing the identity matrix right there, and I really haven't changed anything. That now becomes a placeholder. That identity matrix is what dimensionally? What are the dimensions on that identity matrix? It's n by n. It has to be the same dimension. It has to make sense. Capital X was an n by 1 vector. And if I want to introduce a matrix that doesn't change scalar s times x of s, I need to scale s by this identity matrix that's n by n, and then hit it on the right by capital X of s. Now that I have si in there, I can now combine si with a. So that now I can say, oh, I now have si minus a times capital X of s, and let me put everything else on the other side. I have the initial condition plus B u of s. We're playing with matrices, and now the order with which I multiply and invert is important. And I want to isolate capital X of s, and for that reason I want to now multiply everything on the left by this quantity si minus a inverse. S is a scalar, that's our frequency variable. And if I operate on the left by si minus a inverse, I end up with capital X of s, and over here on the right I have si minus a inverse x of 0 minus, whoops, plus si minus a inverse b u of s. Now I'm getting close to where I want to be. I have an expression for capital X of S. Let me now look at the output equation. And if I Laplace transform that, in general, let me go ahead and say y of t is now the Laplace transform of cx of t plus d u of t in general. And that now says that y of s is equal to c capital X of s plus d u of s. Since everything is at the same time, that's a pretty clean transform. Now what I'm going to do is I'm going to replace that capital X with what I just found it to equal up above from the dynamic equation. Plugging all of that in, I now have y of s is equal to c times the first piece, which is this si minus a inverse x of 0 minus. And then I have the second piece of that, which is c si minus a inverse b u of s. And then I need to keep track of this last piece, which was the d u of s. And that's now my Laplace transform of that system, or that dynamical system, which contains some dynamics, x dot or x prime equal ax plus bu, and y is equal to cx plus du. This is now the frequency domain expression to that, and in this particular form, hopefully it's clear that I have actually two parts to that output. I have an initial condition part, which would give rise to the initial condition response, and then I have a term that's due to the forcing function, the input. So now I've separated, or I can identify the output in terms of two pieces, an initial condition piece and a forced piece. What we want is to look only at the forced piece, since we're going to neglect initial conditions, and we just want to know what's the transfer function between the input u and the output y. Meaning for now, to get that transfer function, we can neglect or will neglect the initial condition piece. But if you wanted the total solution, there it is. You just have to inverse Laplace transform that capital Y of S to obtain little y of t. And that would include the initial condition response and the forced response. If we want just the transfer function, we're neglecting the initial conditions. We can then set the initial condition to 0, and now we're just left with those two terms that are highlighted with the blue highlighted color. And we now have then y of s is equal to c si minus a inverse b u of s plus d u of s. But if I factor out that input transform, I now have c si minus a inverse b plus d times u of s. And now, if somebody gives you a state space representation in terms of an A matrix, a B matrix, a C matrix, and a D matrix, now you can immediately find the transfer function between the input and the output by substituting those particular matrices into this expression and computing that expression. This is now a symbolic expression in terms of this complex frequency variable S. And in our case, it's a single input, single output system, so we would expect G of S to be a scalar transfer function, a ratio of polynomials in S. And for our mass spring damper system, the D matrix was actually 0, and so that relationship simplifies even more. Let's look at our particular example and see if we can come up with the same transfer function that we started with, or we've already obtained, two different ways. So for our example, D is equal to 0, and we now have G of S is equal to C SI minus A inverse B. Let's plug in what we know. We know the output matrix was 1, 0. We know that this next piece was S times I, and I we said was n by n. In our particular example, little n was 2, so this is a 2 by 2 identity matrix. Then we subtract our A matrix, which was 0, 1 minus K over M minus B over M. And we invert that. And then we multiply it by the input matrix B, which was 0 gamma over M. And that now should be the same as our transfer function that we've derived many different ways. And you can probably do that in your head. Yes? That's now a 2 by 2 matrix invert symbolically. On the exam, I'll probably give you a 5 by 5 that I'll need you to symbolically invert. Oh, you want a 6 by 6? Okay. So 5 by 5 might be a little trivial, so we'll start with a 6 by 6. I have drop add forms too, if you need those for now. Let's just look at how easy this is. Well, let's just do it at least once. Now the S times the identity matrix is going to be S0, 0S. So let me just do the inverse first. Let me push that negative sign in to the second matrix, and I now have 0 minus 1, and I have a K over M and a B over M. And I want to now invert that. And let me just combine those two matrices. I can add those, and I now have S. I have a minus 1. I have a K over M, and I have an S plus B over M, and I now need to invert that. And what's the inverse of a matrix? It's 1 over the determinant of that matrix times the adjoint matrix, which is the cofactor matrix transposed. Not a problem. So let's start with the determinant. The determinant, especially in a 2 by 2, and the determinant of higher orders is just basically you just boil it down. You can expand about a different row or a column, and you can end up with just 2 by 2 determinants. So this is the main piece of all of those calculations. We take the diagonal and multiply those together and subtract the product of the off diagonals. So I subtract a minus K over M. There's 1 over the determinant, and now I need to multiply that. That's what that little dot symbolizes. That's going to go here. And now I need to find the cofactor matrix. I'm sorry, the adjoint matrix, which is the cofactor matrix transposed. And the way that I do that is if I want the cofactor matrix, I simply eliminate the first row and the first column if I want the 1, 1 cofactor, and I find the determinant of what's left over. And in this 2 by 2, that's pretty easy because what's left over is a scalar. So what's left over is just the S plus B over M. But in general, if this was a 3 by 3, If I wanted the 1, 1 cofactor, I would eliminate the top row, I would eliminate the first column, and I would take the determinant of what's left over, which would be a 2 by 2 matrix, and I could find its determinant, and that would be then the cofactor of that 1, 1 entry. And then what I want to do is transpose that to give me my adjoint matrix. But everything on the diagonal, when I transpose, stays. And I just flip across the diagonal when I transpose. That's what I'm doing. It's not magic. I'm not shuffling cups or anything. But now what do I have in the 1, 1 entry of this matrix? Should I do the cofactor matrix and transpose it, and then you won't be quite as confused? I'm trying to make this understandable. So let's transpose that. Let's just find the matrix of cofactors. To find the 1, 1 cofactor, I eliminate the first row, I eliminate the first column, and I take the determinant of what's left over. What's left over in this case is simply S plus B over N. That's the determinant of what's left over. Since it's a scalar, I can just take that as my leftover piece. Now, what if I want the cofactor of the 1, 2 entry? I eliminate the first row, and I eliminate the second column. And I take the determinant of what's left over, and I actually need to scale it by a -1 raised to the I plus j power, or the 1 plus 2 power. In this case, what do I have? If you can follow all my highlighting, I now have eliminated, and all I have left is this k over m, and I need to multiply it by -1 raised to the (1 plus 2 power, which will be -1 cubed, or it keeps that -1 there. Now, if I want the 2, 2 cofactor, what's that going to be? I eliminate the second row, second column, and what's left over I take the determinant of, and what's left over? Just S. And if I scaled that by -1 to the 2 plus 2, that's -1 to the 4th, so that -1 goes away, so I don't worry about it, and I now have S. Now, what's the 2, 1 cofactor? The 2, 1, I eliminate the second row, eliminate the first column, and I look at what's left over, and that's this -1. But I need to scale that -1, so I start with -1, but I also need to scale that -1 raised to the 2 plus 1 power. I now have -1 times a -1, and that will just become 1. If I do all of that, and can I simplify this a little bit? I'm going to say that this piece here is just delta for my determinant. I now have the inverse of that matrix is 1 over delta times the transpose of what I just found, which was the cofactor matrix. This 2, 2 piece flips, the 2, 1 piece flips and becomes the 1, 2 piece, which was just 1 when I had -1 times -1. The minus k over m plops down there, and the s is right there. Now, if you look carefully at what you just had found and compare that with the original matrix, you might see a relationship, and it holds for a 2 by 2. So if you need to invert a 2 by 2 matrix, you flip-flop the diagonal terms and you change the sign of the off-diagonal terms, and that's your matrix of that's your adjoint matrix. Meaning this matrix was just the original matrix that I was trying to invert here if I just flip-flop the diagonal pieces and change the sign of the off-diagonal. And now I have my adjoint matrix, and I divide that by the determinant, and that's my inverse of that matrix. All right, that was an aside to get us the inverse of a matrix. Now we need to find the transfer function, which we better determine is the same as what we found the other two places, or doing it the other two ways. I now have C, which was 1, 0. I have my SI minus A inverse, which I just found to be S plus B over M, 1 minus K over M, S, times my input matrix, 0 gamma over M, and I can't forget to divide everything by that determinant 1 over delta. Remember, delta was this piece right there, which was S squared plus B over MS plus K over M. So that's now S squared plus B over MS plus K over M. And now you decide how you want to multiply this. I now have 3 matrices to multiply. I can multiply the first times the second and then the third, or I could multiply the second and third and then the first. It doesn't matter. You should end up with the same result. In this case, it may be easier by pre-multiplying by 1, 0. Really what that's doing is pulling off the top row of that 2 by 2 matrix. That 1, 0 is saying keep everything in the top row and annihilate everything in the bottom row. That's what that 1, 0 output matrix is doing to that 2 by 2 adjoint matrix. So if I simply copy down the top row, I now have G of S as S plus B over M times 1 times this 0 gamma over M times 1 over delta. So I multiplied the first times the second, then I kept the third matrix, which was a column vector, and I still need to scale by 1 over the determinant. But now if I use the same argument, if I look at what's happening here, when I post-multiply by this matrix, or this vector, I'm saying I don't want anything to do with the first column, and all I want to do is pull off gamma over M times the second column, and that's pretty easy to do. 1 times gamma over N gives me gamma over M. That product then simplifies to just gamma over M divided by the determinant. So I end up with G of S is gamma over M over delta, which was gamma over M S squared plus B over MS plus K over M, and that better be the same as what we had before. So now if you don't believe what you've done, do it another way and see if you get the same result. And then sleep on it and do it again another way and see if you get the same result. And then you start convincing yourself, yeah, I think I'm okay with what I've just derived. And that's sort of what we've done. We skipped the sleep. Well, you guys slept through some of that. But now wake up, and now you can see the result 3 different times. Let's look at a Bode plot for this system. And just for grins, let's change it up a little bit. Last time we picked a half a gallon of milk. Let's throw that away. Okay, you guys didn't like that, so let's cut that in half. Let's just use a quart of milk, roughly. Which is meaning 1 kilogram, right? M equal 1. So let's find the Bode plot of this system by setting M equal to 1. Let's say B is 2. Let's say our spring is 1, and let's say gamma is 1. This is going to make our G of S. If we now plug those in, All those m's go away if I let m equal 1. And now I have 1 upstairs. And downstairs I have s squared plus 2s plus 1. And that's a completely different transfer function than what we looked at Friday. Quite a bit different. What was our natural frequency Friday? Square root of 350, I think, wasn't it? So about 18.7 if my memory is serving me correctly. So that was our natural frequency. What's our natural frequency for this system? It's 1, isn't it? It's omega sub n squared is 1, so omega sub n is 1. Here we have a slower system and we have a much more damped system because our damping factor is 2, and now we have this much more damped system to deal with or to play with. What does this system look like in terms of poles and zeros? What's my DC gain? 1. This one is 1 because I just look at G of S equals 0 and it's 1 over 1. The DC gain is 1, so I'm going to be 0 dB, and then I'm going to actually, if I look at this, I really don't have a natural frequency. Well, I have 2. What do I have? How many finite zeros do I have? 0. I don't have any finite zeros. There's no value of S, finite value of S, that causes G of S to go to 0. So they're in the numerator. If I looked for S's, I wouldn't find any, and I'd say, oh, there's no finite S's, or no finite zeros. So I don't have any of those, but I do have 2 roots in the denominator. And what are they? These are real and equal, aren't they? These aren't complex. So I now have 2 real equal roots at s equal minus 1, meaning my denominator looks like that. Which, if I now wanted to sketch that as a Bode plot, magnitude-wise, I'm 0 dB until what point in frequency? So if this is my frequency axis, then I'm going to be flat at 0 dB until I reach what point or what frequency. When I hit a pole, then I have to say, oh, I'm somewhere exciting. I'm going to have to brake. And if I'm a pole, I'm downstairs, I'm going down. And I actually have 2 that occur exactly at the same place. Right here at omega equal 1, I'm going to go down twice what I would for a single factor. A single factor would be minus 20 dB per decade. Now I double that, I'm minus 40 dB per decade. So I'm flat, and then I hit omega equal 1, and now I'm going down, and I'm sloping at minus 40 dB per decade. And that's the straight line approximation. If I wanted to look at the exact form, I would actually be, in this case, since it's 2 real poles, I would have a plot in a MATLAB sketch, or a MATLAB plot of that would look more like this. It wouldn't have that bump because these are now right on the real axis and there's no ringing. These are critically damped poles. And so now I have that nice smooth behavior in the Bode plot, magnitude response. What's the angle look like? if I said, what's my angle at low frequencies, what would you say? If I put in a very small frequency input, sinusoid into this system, let's say a sine of 0.01 radians per second, I excite it with this slow moving sinusoid, what am I going to see at the output? So now I shake this system. If I hit it with a DC value, what would I see? If I hit it with a 2, we said the DC gain was 1, I'm going to see a 2 out, aren't I? Now, if I slowly shake this system, what am I going to see at the output? How's this system going to shape what I'm doing to it if I'm doing it slow? It's not going to have much influence, is it? I'm going to pretty much see what I'm putting in, right? Because I'm at low frequencies, my amplitude is 0 dB, so that means don't change, don't attenuate, don't amplify what's happening at low frequencies. So I'm going to see pretty much what I put in at low frequencies. And I'm going to be lined up. My peak is going to be the peak. I'm not going to have any phase shift, because if I looked at low frequencies, my angle is 0 degrees. At high frequencies, it's going to be what? I'm trying to get the phase plot, and I'm running out of time. Sorry. So here is my phase plot. There's 0 degrees. That's where I start. And where do I end up? I'll give it away. Minus 180. And what happens? A decade before I start transitioning, a decade after, in our approximation, we're done transitioning, and so now I'm here, then I go through minus 90 degrees, and then I'm there at minus 180. So this is supposed to be minus 90 degrees, and this was supposed to be, so I'll line it up. That's supposed to be omega equal 10. That's my straight line approximation. We'll have to start with our 3-mass problem on Wednesday.